In some processes, it's important for the control system to quickly stop any deviations in a process variable from set point. Now, one type of controller that can do this is a proportional plus rate, or rate controller. A rate controller projects how much the process variable will deviate from set point in a given period of time. When input to the controller changes, the controller measures the speed of the change and then produces an instant boost to its proportional output. This boost in the controller's corrective output enables the control system to quickly stop the process variable from changing. Now, rate controllers aren't all that common, but they are utilized in some control systems. In this part of the program, we'll see how a controller's internal mechanisms can be arranged to enable it to provide rate action. Then we'll compare that to an actual rate controller. We've modified the basic controller illustration so that the controller has the ability to provide rate action. We've added two bellows to the controller, both of which are located to the left of the pivot. There's a variable restriction in the line from the lower to the upper rate bellows. The controller's input is now fed to the input bellows, the lower rate bellows, and through the variable restriction to the upper rate bellows. As you can see, the lower rate bellows is closer to the pivot than the input bellows. So for a small amount of movement of the lower rate bellows, a large amount of movement is produced by the beam. This enables the rate controller to boost its output instantly when a process variable deviates from set point. The variable restriction affects a typical rate controller differently from a reset controller. If input increases, both the input bellows and the lower rate bellows expand, bringing the flapper closer to the nozzle and boosting the controller's output instantly. The upper rate bellows pressurizes later than the lower one because the controller's input is delayed by the variable restriction. When input fully bleeds into the upper rate bellows, it provides a force that stops the initial boost in the controller's output. This is true because the force of the upper rate bellows effectively nullifies the force of the lower rate bellows. At this point, the process variable has stopped changing, so rate action stops. Now, at the same time this is happening, the feedback bellows expands due to the change in output. After rate action has stopped, the controller will act like the proportional controller we examined earlier in this program. The variable restriction to the upper rate bellows can be adjusted, just like the reset adjustment we looked at in the reset controller. On a rate controller, this adjustment is called a derivative time adjustment. A derivative time adjustment determines how much rate action the controller will provide. If the restriction is opened, less rate action occurs because the upper rate bellows expands with the lower rate bellows. So the lower bellows can't do what it's supposed to do, cause the beam to pivot and provide an instantaneous boost in the controller's output. Closing the restriction increases the amount of rate action. The lower rate bellows can now expand with very little opposition and provide the boost necessary to catch deviations in the process variable quickly. The important thing to remember about rate controllers is that they're designed to respond quickly to deviations in a process variable from set point. The response takes the form of an immediate boost in output, which stops the process variable from changing. Now, this controller is designed to provide rate action. Now, as you can see, it has several interconnected links and levers, all of which make it hard to see how the controller operates. To understand it better, let's use a simple illustration. This one looks quite different from the basic illustration we just discussed, but we'll see how the controller can provide rate action. Its input mechanism is a board-on tube. This is the set point adjustment. Turning this knob adjusts a link and lever assembly connected to the board-on tube so that the measured input signal is compared to the desired set point. If the assembly were to move, it would mean that the process variable had deviated from set point. Any movement of the link and lever assembly repositions a flapper relative to a nozzle. The flapper-nozzle arrangement is the error detector mechanism. Both the flapper and nozzle are mounted on a rotating disc, which is the proportional band adjustment. When the disc is rotated, it changes the position of the flapper, which affects the amount of output that is produced by the controller. A relay converts changes in back pressure to changes in output, which are fed to a volume chamber. The volume chamber restricts the controller's output signal from being fed to the feedback bellows. If the output signal were to increase, the bellows inside the chamber would expand, restricting the output signal path to the feedback bellows. This delay would prevent the feedback bellows from balancing the movement of the input mechanism. When the output is delayed in reaching the feedback bellows, the flapper can remain close to the nozzle. This enables the controller to provide a boost in its output, which is the essential characteristic of rate control. This restriction is the controller's derivative time adjustment, which varies the amount of rate action the controller will provide. In this segment, we've looked at an example of a rate controller. In general, rate controllers project how much a process variable will deviate from set point in a given period of time. Then the controller produces a corrective boost in its output. This feature enables a rate controller to quickly stop a process variable from changing. Now's the time to read the material in your text dealing with rate controllers. When we return, we'll look at a controller that provides all three control modes we've studied so far. Up till now, we've examined pneumatic controllers that provide just one or two control modes. We'll look now at a controller that provides all three modes: proportional, plus reset, plus rate. Now, this type of controller is commonly referred to as a three-mode controller. A three-mode controller incorporates proportional action to match changes in a process variable, reset action to eliminate offset, and rate action to quickly stop deviations in the process variable from set point. Now, before we look at this controller in detail, let's go back to the controller illustration we've been using and see how all three control modes can be performed by one controller. As you can see, we've included all of the mechanisms we showed separately in one illustration. Two rate bellows and a variable restriction enable the controller to provide rate action. And a reset bellows and another variable restriction enable it to provide reset action. Otherwise, the rest of the illustration is the same as the P-only controller we looked at earlier in this program. Now, to show how this controller provides proportional plus reset plus rate control, let's look at how it reacts to an increase in input. Both the input bellows and the lower rate bellows expand. Since the lower rate bellows is closer to the pivot than the input bellows, the beam pivots sharply, moving the flapper closer to the nozzle. When this happens, the controller's output is immediately boosted to stop the process variable from changing. This is the controller's rate action. As input fully bleeds into the upper rate bellows, it provides a force opposing the force of the lower rate bellows. At this point, the process variable has stopped changing, so rate action stops. Now let's trace what happens on the other side of the pivot. As the controller's output increases, it's supplied to the feedback bellows and to the reset bellows. The reset bellows provides an opposing force that counters the force of the feedback bellows as it expands. As a result, the normal balancing action of the controller is disrupted. The flapper is moved closer to the nozzle, causing the controller to continually increase its output for as long as the process variable is away from set point. This is the controller's reset action. As long as the process variable is away from set point, output will continue to bleed into the reset bellows, forcing the flapper closer to the nozzle and increasing output. The increase in output is fed to the system's final control element, which causes the controller to return to its initial balance position. In this position, the controller's output keeps the process variable at set point. Once again, let's compare the basic illustration with an actual three-mode controller. Now, this controller looks a little different from the illustration, but it contains the same basic mechanisms. To make it easier to understand, let's examine a simple illustration. First, let's see what's similar. Input enters the controller through this port, and output leaves the controller here. This controller has an input mechanism, which is one of 4 bellows. It's referred to as the A bellows. It also has an error detector, a flapper nozzle arrangement, and an output balancing mechanism, which is another bellows called the D bellows. What makes this controller different from the simple illustration is that there are 2 beams and 2 bellows. The bellows are labeled B and C. The B bellows is located on the other end of the beam from the A bellows, and the C bellows is opposite the D bellows. If input changes, the B and C bellows act on the 2 beams to move the flapper and nozzle closer together. This boosts the output, so the B and C bellows are initially the rate bellows. Then, after the input stops changing, the C bellows becomes the reset bellows. The beam attached to the A and B bellows is connected through a linkage to the flapper, and the nozzle is mounted on a beam supporting the C and D bellows. Set point is adjusted by increasing or decreasing the tension on these 2 springs, each of which is located on a separate beam. Let's go through the 3-mode controller and see how this all fits together. We'll discuss how the controller provides proportional plus reset plus rate action in response to an increase in input. The controller's input is fed to the A bellows and to the C bellows. If input were to increase, this beam would overcome the tension of the set point spring and tip in this direction. And this beam would pivot in this direction. As a result, both the flapper and nozzle move towards each other, providing an immediate boost in output. This is the controller's rate action. Input also bleeds from the derivative time adjustment here into the B bellows, which exerts a force on this beam opposite to that of the A bellows. This would cause the flapper to move away from the nozzle. When the input to the controller stopped changing, pressures to the A and C bellows would also stop changing, signifying that the controller's rate action has stopped. Well, now let's concentrate on how the controller provides reset action. The D bellows is the feedback bellows. It would pressurize as output increased in an attempt to rebalance the controller. This would cause the beam to tip in the opposite direction, as was the case when the C bellows expanded, and attempt to pull the nozzle away from the flapper. But the increase in output is also fed through the reset restriction here and bleeds into the C bellows, which now becomes the reset bellows. The increase in the controller's output would keep the C bellows pressurized so that it would exert an opposing force on the beam from the D bellows. In effect, the C bellows would keep the nozzle close to the flapper. This would tend to increase the controller's output and therefore enable it to provide reset action. The output would continue to increase until the process variable returned to set point. This controller, like many 3-mode controllers, has a number of different switches and adjustments that are covered in your text. It's important to make sure you have the switches and adjustments in the right positions. Otherwise, the controller won't provide the appropriate control mode for a process. Make it a habit to read the manufacturer's instruction manual before you work on any controller or tune a control system. In this program, we've looked at several different types of pneumatic controllers. We've seen how their internal mechanisms are arranged so that they provide different control modes. In your job, you'll be responsible for maintaining several types of pneumatic controllers, some of which may not look at all like the ones we've examined in this program. But you can apply the knowledge you've learned here to virtually any controller. No matter what a controller looks like, it has 3 basic mechanisms: input, error detector, and output balancing. In addition, it'll perform 4 basic functions: measure, compare, compute, and correct. At this time, read over the text material on 3-mode controllers. Then go back over any of the other sections if you need to. Be sure you have a good understanding on the principles of operation of basic types of pneumatic controllers.